So in this video, we're going to look at problem 4.10 from the homework. We have a beam which is suspended to the wall. There is a 500 Newton force exerted at the end of the beam, which is defined geometrically by an angle theta from the horizontal. And what we're asked is, if we know the actual width of the beam, d, to be 0.26 meters, can we find the angle theta such that the moment of this 500 Newton force about point B is 0? So that's a lot of words going on in the description, especially if you're still a little bit fuzzy about the content that we discussed in lecture last week from chapter 4. So let's kind of break this down step by step. So first and foremost, you see the word moment. So what does the moment of a force about a point actually define? Remember that the moment of a force about a point is going to define the tendency of that force to induce rotation of the body about that point. And I'm just going to leave the the body part out, about that point. So remember that we talked about two different approaches. The first approach that we talked about was a scalar. Man, I am not spelling well today. Hopefully no one is spell checking me as you actually watch this video. The first approach that we talked about was the scalar approach. And the second was the actual vector approach that used the cross product. So I think this problem is easier to do via the scalar approach. And remember that when you take the scalar approach, there's really a two-step process. The first thing that you need to do is to determine the sign, SIGN, of the moment. And remember that in that case, and particularly here, I'm talking about, usually you would only apply the scalar for a 2D force system. And in a 2D force system, the moment, of course, is a vector, and its direction is always going to be, for a coplanar or 2D force system, defined by the z-axis. So the only question is it counterclockwise rotation about the z-axis or clockwise rotation about the z-axis? So that's what we actually mean by the sign. Remember, the convention is counterclockwise rotation about the z-axis is denoted as a positive moment, and clockwise rotation is denoted as a negative moment. And then once you've actually determined the sign of that moment, we'll determine the magnitude, and that is going to involve actually computing, which we're usually given the perpendicular distance. And in most of the problems, example problems that we work, the perpendicular distance will involve, it will be most easy to get if we decompose the force into components initially. So that's actually how I'm going to go about solving this problem. Step one, I'm going to decompose that 500 Newton force into rectangular form. I can just say X and Y components. And this is a pretty easy problem to see how that decomposition would work. I can just take and I'm going to intentionally draw my components using different colors in this case. So that is the X component of the 500 Newton force. And I can write it easily. Notice that it is adjacent to this angle theta. So it's just going to be 500 cos theta. And it's pointing in the positive direction. But remember that when we use kind of the scalar techniques to computing moments, we don't worry necessarily about attaching a sign to the actual components of the force. We deal with the sign when we actually determine the direction of the rotation that it causes, which was step one here. So I'm going to decompose and show the actual Y component of the force. And notice that in terms of magnitude, of course, it would be opposite of that angle theta. So it's going to be 500 sine theta. And if we were actually writing it in rectangular form, we would add on a negative value to show that it points in the negative direction. However, I'm not going to worry about that for now. Remember that when you take the approach of computing the moment using a scalar approach, that oftentimes it's nice to actually extend out your line of actions of your forces. It will allow you to easily see what the distances are that you need in order to compute that perpendicular distance, which is necessary to get the magnitude. And so we're going to start by looking at, after we've done the decomposition here, which we have, step two, we'll actually begin with computing the moment of, and we can pick either one, but I'll say the X component. So when you're computing the moment of a force about a point using the scalar approach, the first thing that you want to do is define the direction, which is just going to be expressed by the sign that describes whether the rotation that's induced is counterclockwise or clockwise. And the way that you're going to do that is pick the point about which you're calculating the moment, which is B. In this case, take the force that you're actually considering, which is the X component, and actually pin the paper down at point B and pull the paper in the direction of the force. And I'm doing too good a job of pinning it down, but if you notice, if you pulled in the horizontal direction, if the paper is pinned here, that's going to be a counterclockwise rotation. So this is counterclockwise rotation. So by convention, that is a positive moment in terms of describing the direction of rotation about the z-axis. B, all that we need to do is find the perpendicular distance next. Remember that in order to find the perpendicular distance, you're just asking yourself from the point of interest, which is here B, you can draw a ton of different lines to the line of action of the x component of the force. However, there's only one that you can draw that will intersect the line of action in a perpendicular fashion. And that's going to be a purely vertical line. And notice that we're told that it is of length d. And we're given the actual value here, 0.26 meters. However, for now, I'm just going to express it in terms of d. So the perpendicular distance is d. So thus, I can compute the moment of the force Fx about point B is just going to be add in the plus or minus depending on the sign. Since it's counterclockwise rotation, it will be plus. Add in the magnitude of the force. It's going to be 500 cos theta. That's the F component. And then add in the perpendicular distance, which in our geometry is just going to be d. So now that I've done that, I will actually do the y component. So I'm going to, since this is all in the same step, I'll say now let's do Fy. So let's use that same kind of logic. Let's begin by finding the direction or the sign that describes whether the rotation caused by the y component is clockwise or counterclockwise. So again, I'll pin at point B and I'll pull my paper in the direction of the y force. And this is why you actually don't add the negative in here. It just confuses the point. A force in the downward direction about point B is going to induce an actual clockwise rotation. And by convention, clockwise rotation is denoted with a negative sign. So if you notice, kind of the actual manual inspection of the direction of the rotation is taking care of itself here, because the rotation caused by the x component is going to counterbalance or go in the opposite direction of the rotation caused by the y component. So that's why these have opposite signs in this case. Step B, I need to find the perpendicular distance. So I'm going to go from my point of reference, which was B, and I'm going to ask myself, of all the different lines I can draw to the line of action, what's the only one that will intersect it in a perpendicular fashion? And that line is simply a line that goes directly along the beam. So notice that this dimension in this case is nothing more than 2. So the perpendicular distance is nothing more than 2 meters. So next, I will finally compute the moment of that y component about point B. It's just going to be the magnitude of the force, which is 500 sine theta, multiplied by the perpendicular distance, which is 2. And don't forget to actually put a negative in front, since that rotation is in the clockwise direction, which is negative by convention. So I'll just write it out a little bit clearer here. This is going to be minus 500 sine theta times 2. So that's the kind of FD formulation that you see in the textbook. Now you might ask yourself, well, why didn't Henry just multiply the 500 times 2 and make it 1,000? Well, here's the reason, right? So for step 3, I know that since moments are vectors, I can find a resultant moment or actually add those together. The moment of the entire force F is going to be nothing more than the moment of the x component plus the moment of the y component. And I want these to be 0. That's what I'm actually interested in happening. So taking the expression for the x component that I have from part 1, 500 cos theta times d, and then adding on in an actual vector fashion the expression for the y component, which is going to be minus 500 sine theta times 2, I want that whole thing to equal 0. So if I actually manipulate this equation, then I'm just going to write the entire thing in black now, and I'm going to grab a little bit of an additional piece of paper. Sorry about the confusion. Hope I'm not making you ill watching me move the documents on my .cam. So just actually moving this negative term to the other side, I'll get that 500 cos theta times d equals 500 sine theta times 2. So what I'm going to do is just cancel that factor of 500 from both sides of the actual equation. And what that's going to give me is d cos theta equals 2 sine theta. Remember, what we're actually trying to solve here is theta. And usually when you have this, what's known as a transcendental equation, an equation that actually involves trigonometric functions, you try to take the ratio of them in order to get a single trigonometric function. In this case, the easiest one to do is sine divided by cosine. And then you will isolate the variable that you're trying to solve for, which is theta, by taking an inverse trig function. So how do I actually do that? Well, notice I'm going to divide both sides by 2 to start off with. So this is a d divided by 2 cos theta equals sine theta. And then I'm going to divide both sides by cos theta. And what that's going to give me is that d divided by 2, and d is just that dimension of the width of the actual beam, is equal to tan theta. So this is what I'm actually interested in solving for. It's inside the argument of my tangent function. So what I'm going to do is take an inverse tangent. I'm just going to show this because I got a question about it, and I think it confused some people. So if the definition of the inverse tangent function is it undoes whatever the tangent does, if you take the inverse tangent of the tangent, it's just going to leave you with, and I should have, bad job on me. Remember, I just can't take the inverse tangent of one side of the equation. If I do that on one side, I also have to do it to the other. That's what I get for trying to explain before I actually look at what I'm writing. So on this side, inverse tangent of theta is just going to leave me with theta. And I'm going to be able to compute what that angle needs to be by simply taking the inverse tangent of d over 2. So actually putting that in a calculator, theta is going to be equal to, we were told that d in this case is 0.26. So if I take and I just divide 0.26 divided by 2, and I'm going to go and make my computation here in MATLAB. So I will say a tan d of 0.26 divided by 2. The d tells me that I actually want the answer in degrees. So rounded to 3 sig figs, I get that theta equals 7.41 degrees. Now let's actually see if we can make some intuition out of this just from a physical perspective. That's a relatively small angle, right? 7.41 degrees, which basically means that this force, and I'm going to put it up at the top, has to be nearly perfectly horizontal. Now let's think about the reason that is. When you look at the y component of this force, it has this very long lever arm. The perpendicular distance is really, really big. So you don't need a lot of force in order to induce a large moment about point B. It's kind of like you have a wrench that's very long, so you don't have to actually push on it very hard in order to induce a lot of rotation about B. However, the x component of this force has this very small lever arm. So basically, as the width of this beam is really, really thin, if you don't want to induce any net rotation about point B, you're going to need this theta to be almost 0. And that's exactly what is happening here. If you have a very small theta, the majority of the magnitude of this force is going to be in the x component, not the y component. And that's needed because basically what these two things are doing is counterbalancing their tendency to rotate about point B. X is inducing counterclockwise rotation, y is inducing clockwise rotation. So then since the y component has the advantage of having a much longer lever arm, you're going to have to, in order to make them equal to each other, make the majority of the force actually directed in the x component. So hopefully this was a helpful video for you and allowed you to refresh the scalar formulation of actually computing moments, and I'll see you in the next video.